Think of energy as the world's currency. It's what makes everything happen. Energy is the fundamental ability to cause change, to make your scooter move, to power a movie, or to help a seed grow into a tree. It comes in countless forms, like the light from the sun, the heat from a fire, or the electricity flowing through wires. Since energy is constantly changing form and moving around, we need good tools to keep track of it. And that's where graphs come in handy. In science, we usually split energy into two main types: kinetic energy, Ke, and potential energy, Pe. Kinetic energy is the energy of motion. Anything that's moving, like a running person or a gust of wind, has it. Potential energy is stored energy, like a ball held high up in the air or a battery waiting to power a toy. Learning to track the movement between Ke and Pe is crucial, and graphs are the perfect way to show that change visually. Why do scientists love graphs when studying energy? Because energy data, especially when it's changing quickly, can be confusing just as a list of numbers. Graphs turn that list into a simple picture. With a graph, we can instantly see if energy is going up, going down, or staying the same. They help us interpret complex information and easily spot patterns, making it much easier to compare one experiment's results with another. One of the simplest ways to display energy data is using a bar graph. Bar graphs are fantastic when you want to compare different amounts. For instance, if you were comparing the total amount of energy produced by different sources, say a solar panel versus a wind turbine over a day, a bar graph would show you immediately which one was the winner. The height of the bar tells you everything you need to know about the total energy output. When we want to show a continuous change in energy, like how the temperature of a cup of water changes as it cools, we use a line graph. The horizontal line, the x-axis, usually represents the progress of the experiment, maybe time or distance. The vertical line, the y-axis, shows the amount of energy we're measuring, perhaps in units called joules. The line graph lets us see the rate of change. Is it slowing down or speeding up? Let's look at a classic example: a skateboarder going up and down a ramp. When the skateboarder is at the very top, just about to start rolling, they have maximum potential energy, Pe, because of their height. If we graphed this, the line for Pe would start high, and as they roll down, the line would drop steadily. The energy is not disappearing. It's being converted into something else. As the skateboarder moves down the ramp, their speed increases rapidly. This increasing speed means they are gaining kinetic energy, Ke. So if we graphed the Ke, the line would start low because they were still at the top and rise until it reached its highest point at the very bottom of the ramp. Remember, Ke is all about motion and speed. At the lowest point, they're moving fastest, so their Ke is maximized. If you put the graphs for potential energy and kinetic energy onto the same display, you'll notice something amazing. They are mirror images. When the Pe line is high, the Ke line is low. And when the Pe line is low, the Ke line is high. This inverse relationship is the key to understanding energy transfer. It's like a sliding scale. As one type of energy decreases, the other type increases by the exact same amount. Another perfect model for energy changes is a pendulum, a weight swinging back and forth. Think about the moment the pendulum reaches its highest point on either side. It stops for a split second, so its kinetic energy is zero, and all the energy is stored as potential energy. Then, as it swings down and moves fastest through the center, the kinetic energy is at its maximum, and its height, and thus its potential energy, is at its minimum. When you graph the pendulum's motion, the lines clearly show this transformation. The line representing potential energy looks like a big U shape. It dips in the middle where the height is lowest. The line for kinetic energy looks like an inverted U. It peaks in the center where the speed is highest. These intersecting lines visually confirm that energy is simply changing forms as the pendulum swings. The most important rule in energy is the law of conservation of energy. This law states that you can't make new energy and you can't destroy old energy. It just changes its form or moves to a new object. When the skateboarder rolls down the ramp, the potential energy isn't destroyed. It's converted to kinetic energy. This law is the reason why your graphs of total energy behave in a very specific way. So, if energy is always conserved, what happens when we graph the total energy of the system? If we could ignore friction and sound, the total energy would be the sum of all the PE and KE combined. Because the loss in PE is always matched by the gain in KE, the total amount of energy never changes. Therefore, on a graph, the line for total energy must be a straight, horizontal line. This flat line is the visual proof of the law of conservation of energy. Sometimes, energy transforms into many different types at once. Take a flashlight. The battery's chemical energy turns into electrical energy, which then produces light energy and heat energy. When showing this kind of breakdown, a pie chart is the best graph to use. It clearly shows the percentage of the original energy that ends up as light compared to the percentage that ends up as heat. This transformation leads to the idea of energy efficiency. Look at that flashlight pie chart again. We want the light energy, but we don't really want the heat energy. That's wasted energy. A graph is an excellent way to show how much of the energy input is converted into the desired, useful output compared to how much is lost, usually as unwanted heat or sound. The more useful output, the more efficient the device is. Let's design an investigation to measure thermal energy change, or heat. We could take a pot of water and put it on a stove. Then, we use a thermometer to record the temperature every minute for 10 minutes. We can then plot this data on a line graph. The temperature on the y-axis represents the thermal energy, and the x-axis represents time. We'd expect the line to go up because the thermal energy of the water is increasing. When interpreting the line graph of the water heating, pay close attention to the slope, or the steepness of the line. A very steep line means the temperature is rising quickly. Energy is being transferred fast. A line that is flatter or has a shallow slope means the temperature is rising slowly. This tells you something about how fast the energy is moving into the water, or perhaps how much thermal energy the water can hold. When interpreting the line graph of the water heating, pay close attention to the slope, or the steepness of the line. A very steep line means the temperature is rising quickly. Energy is being transferred fast. A line that is flatter or has a shallow slope means the temperature is rising slowly. This tells you something about how fast the energy is moving into the water, or perhaps how much thermal energy the water can hold. We can also use bar graphs to represent the potential energy stored in consumables like batteries. Imagine 3 batteries, A, B, and C, each powering the same remote control car. If we track the distance the car travels before the battery dies, we can create a bar graph. The battery that makes the tallest bar travels the farthest, must have had the most chemical potential energy stored inside it, ready to be converted to kinetic energy for the car. The food you eat gives your body chemical potential energy, measured in units called calories. Nutrition labels often use bar graphs to compare the calories in different servings of food, or to break down the energy sources like fats, proteins, and carbohydrates. The tallest bars on these graphs represent the foods that provide the most stored energy for your body to convert into kinetic energy for running and growing, or thermal energy to stay warm. To summarize, energy is the ability to cause change, and it constantly transforms between forms like potential and kinetic. We use line graphs to show how energy changes over time. often seeing the PE and KE lines as opposites. We use bar graphs to compare the total energy in different systems. And always remember the golden rule. The total energy line must be flat, proving that energy is conserved. Graphs are the indispensable tools for visualizing this fundamental principle.